So welcome everyone. Today we have our invited speaker is Théo Simon from University of Montpellier. So he will be discussing how we can constrain cosmological models with the EFT of large-scale structure. So thank you for accepting the invitation, and you have roughly 45 minutes and then a few minutes of discussions. You can start whenever you want. Thank you.
Okay, so first of all, thank you everyone for the invitation, and especially Rodrigo. It's a great pleasure and a huge honor to be here to talk about my work. So yes, my name is Théo Simon. I'm working in Montpellier in the south of France. I'm a second-year PhD student. I'm working with Vivian Poulin. And I'm going to talk about the effective field theory of large-scale structures and how is it possible to use it in order to constrain some cosmological model. So first of all, I'm going to talk about this theory within the lambda CDM model, and this will allow me to explain the self-consistency of this theory, but also the main motivations. And I'm going to rely especially on this first paper, where we have carried out the first EFT analysis of the EBOS QSO data. So if we want to constrain a cosmological model, we can use, for instance, the CMB data, namely the CMB paraspectra from Planck, for instance. And these data are well described within the linear perturbation theory because CMB is really homogeneous and isotropic, which implies that within the linear perturbation theory, we can extract information from the full shape of the CMB power spectrum. Also, we can use, for instance, the galaxy power spectrum from the large-scale structure surveys in order to constrain a cosmological model. And the things are a bit trickier if we want to describe or to extract information from this data thanks to linear perturbation theory consideration. But usually, if you want to extract information from the galaxy power spectrum, there are two popular ways to do that. The first one is to use this formula, which is the Kaiser formula, that allows us to express the linear galaxy power spectrum thanks to the linear matchup power spectrum with a given function, which is the Kaiser function that depends on one parameter, on one bias parameter B1 that we have to fit to the data. This parameter B1 allows us to take into account the specific behavior of galaxies with respect to the whole matter. However, unlike CMB, galaxy is a really non-linear process. So this formula, which is a linear computation, is not accurate enough if we want to describe the full shape of the galaxy power spectrum. So we have a lack of precision with this formula. Unusually, to overcome this problem, the large-scale structure collaborations use a second method in order to extract information from the galaxy power spectrum with two different kinds of information. First, coming from the BAO angle, what I'm going to talk BAO, what I'm going to call BAO in the following. And secondly, from the redshift space distortion information, which is a combination between F, the growth factor, and sigma 8, which is the amplitude of density fluctuation in the small scale. However, with this method, we have this time a lack of information because we extract some part of the full shape and not the whole full shape of the galaxy power spectrum. So to overcome this issue, we can invoke the effective field theory of large-scale structure, which allows us to have a non-linear computation of the galaxy power spectrum. So here I'm showing you the one-loop expression of the effective field theory of the galaxy power spectrum, which depends on terms up to chi-square. So I will not enter too much into details because it's beyond the scope of this paper, of this talk, sorry, but I want to stress here two important things. Is that this formula, this nonlinear galaxy power spectrum at one loop, depends only on the linear matchup power spectrum. This means that we can use a Boltzmann code for instance, the class code or the COM code, in order to compute the linear matter power spectrum. And we can use this computation with this formula in order to obtain the non-linear galaxy power spectrum. So this is something which is really easy to achieve, and also which is really fast and really accurate. The second thing I want to stress is that this formula, unlike the Kaiser formula, which depends only on one parameter, this formula depends on 10 parameters that we have to fit to the data. And we have especially 4 galaxy bias parameters that allow us to take into account the specific behavior of the galaxies with respect to the warm matter. So we have the linear bias, the one of the Kaiser formula, the B1 parameter. And we have also 3 other bias parameters, which corresponds to the nonlinear bias. We have 3 contour terms, which correspond to the contour terms of the theory, which allow us to encode the physics at small scale and its impacts on the physics at large scale. And finally, we also have 3 stochastic terms that allow us to take into account the stochastic behavior of the galaxy distribution. And especially, we have C epsilon 0, which is the usual constant short noise term. And we have also 2 other parameters, which corresponds to scale dependent stochastics terms. So this formula and this theory has already been applied to the bus data, which are divided into 4 sky cuts. I mean, when I say 4 sky cuts, I mean 4 different measurements of the galaxy power spectrum. And usually we decompose this galaxy power spectrum thanks to a Legendre polynomial decomposition to extract the 2 main contributions, which are the monopole and the quadrupole. And here I'm showing you the fit of the EFT as well as the fit of the linear predictions, I mean, with the Kaiser formula of 1 sky cut of the bus data, either for the monopole or for the quadrupole. And we can see that with the EFT of LSS, we have a huge improvement in precision with respect to the linear computation, which is maybe the biggest success of this theory. So regarding the cosmological constraint, we can compare the one of Bose with the one of Planck, and we can say that a Bose alone allow us to determine omega m and h naught with a precision of only 10% and 60% lower than Planck, which is quite significant because this is quite competitive to the Planck data with Bose alone. However, if we want to obtain such constraints, we can use 3 main codes in the literature with 3 different parametrizations of the EFT of LSS. The first code is the class PT code with a given parametrization, the ISCOS parametrization, which is a given parametrization of the effective field theory of large structures. We can also use the Piper code with another parametrization, the West Coast parametrization. And actually, this is the parametrization I showed you before when I talk about the 10 EFT parameters. There is also a last code, but I'm not going to talk about it because we can derive similar conclusion with this code. So here I'm considering the class PT code and the Piper code with 2 different EFT parametrization and with different priors or set of priors on EFT parameters. And it turns out that this difference in priors on EFT parameters leads to a shift in the cosmological results between the different parametrization. So here I'm showing you again the constraint of the Bose data only, so which is the same as the blue contour here. And in the two first line, we have taken the same code, so the PyBird code, with the two different parameterization, the West Coast parameterization and the East Coast parameterization. And we can see that the parameterization leads to a shift up to 1 sigma. For instance, on AS, the amplitude of the primordial power spectrum, and on sigma 8 and on S8, for instance. So this is really significant because here we have two parameterization. So we are using the same theory, we are using the same data, but we have shift up to 1 sigma. And however, if you compare the last two lines where we have taken the same parameterization, but the two different code, then we obtain a very good consistency between the results. So this means that this is not a problem of the code itself. And we have checked that this is not a problem of the theory itself, but this is really a problem of the Bayesian inference itself and a problem with respect to the priors on the EFT parameters. What's happened here is that when you perform an MCMC, the EFT posteriors are highly non-Gaussian, and this will create projection effect in the MCMC. And because you put different priors, then you obtain different projection effects between the different parameterizations. And actually, there are several ways to overcome this problem. The first one in the left panel is to consider a larger volume of data. So here we have taken the CovMat of the BOSS data, and we have divided this CovMat by 16, which corresponds to a volume which is 16 times larger than the volume of BOSS. And this allows us to mimic the future experiments like DAISY or Euclid roughly. And we can see that if we consider a larger volume of data, so this is like mock data from the BOSS data. So if you consider a larger volume of data, then we obtain a really good consistency between both parameterization. This is because here we decrease the error bar of the data. And when we decrease the error bar of the data, we obtain posteriors on the EFT parameter that are really Gaussian, and then we decrease the projection effect in the Monte Carlo. A second way to overcome this issue is to combine the BOSS data with Planck data. And if we combine both data, then regardless of the parameterization we are using, we obtain really consistent results. Also, what we can do is to perform a profile likelihood of the effective theory of large-scale structure of BOSS data, because profile likelihood deals with best fit only, and the best fit are not subjected to such a projection effect. So in the profile likelihood, we impose no priors, and we deal only with best fit. And we are working on it. And indeed, with the profile likelihood, we obtain really good consistency between both parameterization. So now we know how to apply the effective theory of large-scale structure to a given data set. And here in this work, we have applied the effective theory of large-scale structure to the EBOS QSO data. This corresponds to data to quasars selected in the redshift range between 0.8 and 2.2. So this is another tracers than the BOSS data, because this is not galaxies now, but this is quasars, and this is also another redshift. Here, the typical redshift is 1.5, while for BOSS data, the typical redshift is between 0.3 and 0.5. Here, I'm showing you the fit of the effective field theory of large-scale structures, either for the power spectrum in the left panel, or for the correlation function in the right panel. If we want to obtain such good fit, we need to determine the regime of validity of the theory, namely until which Kmax the theory is valid. So here we have chosen a Kmax of 0.24. And to do so, what is really powerful with the EFT of LSS is that we are able to determine the regime of validity with the theory itself. And to do so, we need to add some next-to-next leading order terms to the one-loop order contribution. So these next-to-next leading order terms correspond to the dominant two-loop terms in K square. And here it depends on two new EFT parameters. So here, what we have done is that we have performed two kinds of analysis. An MCMC with the one-loop order only, and another analysis with the one-loop order plus the next-to-next leading order terms for each scale cut. Okay, and we have decided to take the scale cut where the shift between the analysis with the one-loop order and the analysis with the one-loop order plus the next-to-next leading order term becomes really dominant. Because indeed, if the contribution of the next-to-next to leading order terms becomes too large, then this means that the one-loop prediction is not accurate enough and that we have to take into account the two-loop prediction. And this actually allow us to determine the cutoff scale Kmax of the one-loop prediction. And in our paper, we determined that for point 24, we obtain basically no shift in the cosmological posterior between the analysis with the one-loop order and the analysis with the one-loop order plus the next-to-next to leading order term. So this is a way to determine the regime of validity of the theory with some theoretical consideration. But we can also use some mock data. And here we are using the easy mock, which corresponds to mocks that are built to simulate the EBOS observational characteristics. And indeed, we have checked that up to Kmax is equal to 0.24, the best fit values of the effective field theory of large-scale structures are really consistent with the truth of the simulation. So this is another way to check the regime of validity of the theory. So now, to better motivate this theory, the EFT of LSS, here I'm showing you the constraints either for EBOS or for BOS from the BAO F sigma 8 information, which is a standard analysis used by the current collaboration, with respect to the constraints obtained from the effective field theory of large-scale structure. And it turns out that for EBOS data, we can improve the constraint up to a factor of 2, while for BOS data, we can improve the constraints up to a factor of 5, which is, I think, quite significant, and which is a good motivation to use the EFT of LSS, even within the lambda CDM model. So now we can compare the constraints from the full shape analysis of EBOS with the constraint from the full shape analysis of BOS with the standard Planck data. And what is really interesting is that here we obtain something which is really consistent between EBOS, BOS, and Planck, which is, I think, a non-trivial check of the lambda CDM model. Because I said you before, BOS and EBOS data corresponds to two different tracers, galaxies or quasars, at two different redshift, 0.3, 0.5 for BOS, and 1.5 for EBOS. So we have different redshift, different probes, and we obtain something which is really consistent. And especially what is really interesting is that the H0 value and the sigma 8 value of Planck are in between the one of EBOS and BOS. So here, there is no tension between Planck and between the large-scale structure data. So what we can do then, if there is no tension, is that we can combine those data together and to obtain a large-scale structure data set. So here, especially, we combine the full shape of the EBOS data with the full shape of the BOS data with some BAO experiments without an EFT treatment, plus the Pantheon data, which correspond to the CPR. This is not really a large-scale structure data, but here we are constructing a data set which is purely independent from Planck. And it turns out that the combination of EBOS plus BOS improves the constraints over BOS alone. And now we have a precision which is really, really similar to Planck for omega m and H0. And now because we still have a good consistency between our large-scale structure data set and Planck, we can combine them. Here we combine Planck with our large-scale structure data set in red. And what is interesting is that in the H not omega m plan, we can break up the degeneracy in the Planck data with the large-scale structure data. And this allows us to improve the constraints on omega m and H naught by 30% with respect to the Planck data alone. Yes, a small comment on sigma 8 and AAS, which are not significantly impacted by the addition of the large-scale structured data because the constraints are still dominated by Planck. But I think that it will not be the case anymore with the next generation surveys. Yes, so in this work, we have also considered some extensive model to the lambda CDM standard model. And especially here, we have considered first the curvature density fraction omega k. And so here, I recall that the large-scale structure data here in light blue corresponds to the combination of BOSS, eBOSS, XBAO, and Pantheon. And so here we obtain with the large-scale structure data only something which is compatible to the flat lambda CDM model at 1.3 sigma. And especially our large-scale structure constraint from the EFT of LSS is better by 50% compared to the standard BAO of sigma 8 analysis, which is, I think, another good motivation to use this theory, because even with the extensive model, we obtain better constraints. If we combine the large-scale structure data with the Planck data, we obtain something which is really consistent with the lambda CDM model and excludes the slightly favored negative values of omega k by the large-scale structure data and by Planck. We can also consider another extension, which is the dark energy equation of state. And here we obtain something which is really consistent with the lambda CDM model, either with the large-scale structure data alone, or either with a combination of both. I mean, large-scale structure data and Planck. And here we improve the constraint over the BAO of sigma 8 analysis by 20%. We also consider a third model, which is a total neutrino mass. And here, this is really interesting because we obtain a constraint with a large structure data only, which with the large structure data alone, sorry, which is really similar and really competitive to the Planck constraint alone, because our constraints, our large structure constraints, are only 10% weaker than the Planck constraints. And here we improve the constraint over the BAO of sigma 8 analysis by a factor of 18, which is a lot. And we can combine these two data sets, so large-scale structure, our large-scale structure data set with the Planck data set, and in order to obtain a really strong constraint on the sum of the neutrino mass, which is where we can derive an upper limit of 0.09. And actually, this limit this favors the inverse hierarchy at 2.2 sigma, and it's competitive with the current Lyman alpha constraints. And finally, we have considered a last extension to the lambda CDM model with the effective number of relativistic species. And again, we obtain something which is really consistent with the standard model and with lambda CDM model. And here, what is interesting is that with the EFT of LSS, we are able, even if the constraint is not insane, but we are able to constrain this parameter, while this is not the case with the BAO of sigma 8 analysis. Because BAO of sigma 8 is only sensitive to the background radiation energy density, which is subdominant in the late universe. So basically, this data, this information, the BAO of sigma 8 information is not able to tell something about the amount of radiation in the universe, in the early universe. While with the full shape analysis, we can see the effect on a large scale of this radiation, of the effective number of relativistic species. And here, if we combine with Planck, we obtain also a better constraint. So here, I'm going to give you a partial conclusion of this first part. So we can say that the EFT of LSS provide an accurate description of the large structure data, and that we can control the precision and the regime of validity of the theory. We obtain constraints that are competitive with CMB data, and we improve the constraint with Planck alone when we combine with Planck. In this work, I think we have derived two important conclusions. The first one is that there is no tension between the clustering data and the Planck data. And the second one is that we obtain a strong constraint on the canonical extension to lambda CDM model, and that everything is consistent with a flat standard lambda CDM model. So now the question is that, so okay, the EFT of LSS can provide a strong constraint on canonical extension to lambda CDM, but now does EFT of LSS provide interesting constraint on non-trivial extensions to the lambda CDM model? So here I'm going to deal with a non-trivial extension to the lambda CDM model, which is the decaying dark matter model. And I'm going to talk about the EFT of LSS constraints on this model. So this model has been proposed in order to solve the so-called SA tension. So I'm going to briefly recall what this tension is. So the SA parameter depends on two parameters, omega m, which is the current abundance of matter, and sigma 8, which is the amplitude of density fluctuation in small scale. And this corresponds theoretically to an integral over the linear mature power spectrum times a window function, which allows us to define a sphere of 8 megaparsec. So this parameter is an integral of the linear mature power spectrum within a sphere of 8 megaparsec. And it turns out that within the lambda CDM model, we have a tension in this parameter. We have a tension between the Planck or the CMB determination of this parameter, assuming the lambda CDM model, and between the late time determination of this parameter, which is a direct determination, especially from the weak lensing. And we can use actually the so-called 3.2 statistics in order to combine the information from the 2-point correlation function of the weak lensing with the 2-point correlation function of the clustering in order to break up the degeneracies between sigma 8 and omega m. And we can see that this is more a tension of sigma 8 than a tension of omega m, which is really consistent with the Planck data. So this SA tension is finally more sigma 8 tension. And if we want to solve this tension, then we need to find a mechanism that suppressed the linear mature power spectrum within this sphere of 8 megaparsec in order to decrease this integral and to decrease the CMB value of this sigma 8 parameter to bring back into agreement both determination, especially between Planck and the weak lensing. So we can realize such a suppression with several models, like the warm dark matter model, for instance, but now it has been excluded by the Lyman alpha. We can also consider interacting dark matter, for instance, and we can consider decaying dark matter. And I'm going to talk about this model now. So here, this is the first model of decaying dark matter I'm going to talk about. And this is the decaying cold dark matter to dark radiation model. So this model is an extension to the lambda CDM. And here we add a new assumption is that a part or a fraction of the total cold dark matter undergo at some point a decay into dark radiation particle. So this dark radiation still belongs to the dark sector. I mean, this is something which is not visible, but it's something that still belongs to dark sector. And this model corresponds to the lambda CDM model plus two new parameters. So we have tau, which is the half-life of the dark matter particle, And we have F, which is the fraction of this decaying cold dark matter with respect to the world dark matter. So we can also determine the homogeneous Boltzmann equation either for the DCDM species or for the dark radiation species. And actually, the left-hand side part of this equation corresponds to the standard homogeneous Boltzmann equation for matter or for radiation, where we add in the right-hand side a term that takes into account this decay process. So what is really important to understand here is that at the perturbation level, we are using, because we are using the synchronous gauge that co-moving with the decaying cold dark matter and the standard cold dark matter also, then this means that the decaying cold dark matter perturbations are unchanged in the sense that they are similar to the cold dark matter perturbation. So we have two species, the standard cold dark matter, the decaying cold dark matter. Both are cold, both are both evolve similarly, and we have the same perturbation equation for both. We just need to add the perturbation equation for the dark radiation species, but this is something which has a minor effect on the power spectrum. So here, the effect is dominated by the decrease of omega m at the background level. So omega m is the background quantity. So the main effect of this model is a background effect by decreasing the amount of matter because of the decay process. So here I'm plotting the residuals between this model and the lambda CDM model for the monopole of the galaxy power spectrum for several values of tau and f. And on the left panel, we can see that tau controls the suppression of the galaxy power spectrum. So the lower tau is, and the greater the suppression. Because if tau is low, then this means that you will produce a lot of dark radiation particles really early in the universe, and that you will decrease the value of omega m really early during the history of the universe. And similarly, F controls also the suppression of the power spectrum, of the galaxy power spectrum, and this time the higher F is and the greater the suppression. Because if F is high, then this means that all the dark matter, the standard dark matter, will undergo this decay, and then you have something, you will create a lot of dark radiation particles, and you will decrease significantly omega m also. So regarding the cosmological constraints that we have derived in this work, here I'm comparing the constraint from Planck, Pantheon plus XBAO, with either the BAO F sigma 8 information or the EFT of LSS information of the Bose data. So here, for BAO F sigma 8 or the EFT analysis, we are using only the Bose data because at this point, the full shape analysis of the eBOS data was not available. So here we can derive several conclusions. The first one is that we derive here the most up-to-date constraints on this model, and especially we have derived a lower constraint of on tau, and to do so we need to set f equal to 1 to derive, because if f is equal to 1, then this means that you need a huge value of tau, and this allows us to define a lower limit on tau. And if we consider a small decay constant, then we can derive an upper limit on the f parameter. Okay, but here, as we can see, the EFT of LSS does not improve the constraint over the BAO F sigma 8 because we have roughly the same constraint between the blue and the red control. So for this model, the BAO F sigma 8 information is sufficient to derive the stronger constraint we can with the Bose data. And finally, as we can see, this model does not resolve the SA tension because there is no overlap between the parameter space of this model and the direct determination of the S8 from KIDS and DES. So this model does not resolve the S8 tension for a really simple reason. Because as I told you before, this is the main effect of this model is a background effect. It decreases the value of omega m. However, omega m is really, really well constrained by all the data probes. It's well constrained by Planck, by Pantheon, by BOSS, by the BAO, by everything actually. So we cannot do whatever we want with this parameter. And actually, because this parameter is well measured, then we cannot find a point in the parameter space that can resolve the S8 tension, because we cannot decrease this parameter significantly. So if we want to find a way to solve the S8 tension, then we need to find an effect which is not a background effect, but which is an effect at the perturbation level. So this is why we consider another decaying cold dark matter model, which is this time the decaying cold dark matter to warm dark matter plus dark radiation model. This is also an extension to the lambda CDM model. And here we consider another kind of process where the decaying cold dark matter decays into warm dark matter and into dark radiation. So we have two daughter particles in this model. So this model corresponds to the lambda CDM model plus two new parameters, where we have tau, which is still the half-life of the dark matter mother particle, and now we have replaced f, the fraction, which was a fraction of decaying cold dark matter to the total dark matter, to epsilon, which is now the fraction of the rest mass energy of the decaying cold dark matter converted into dark radiation. So this is the amount of energy transferred by the mother particle to the dark radiation particle. And especially in this model, all the cold dark matter undergo this process. So there is no fraction of dark matter, but really all the cold dark matter is composed by this cold dark matter, decaying cold dark matter component. Again, we can derive the homogeneous Boltzmann equation, and especially here we have the same equation for the decaying cold dark matter and for the dark radiation species as before, but we just need to add this epsilon that allows us to take into account the fact that now only a fraction of the energy is transferred to dark radiation, and not all the energy as before. And we can also derive the equation for the warm dark matter, but this time we need to keep the equation of state parameter of the warm dark matter inside this equation, because we don't assume that this particle is relativistic or it's purely cold. It could be between both. And what is really interesting is that now this model is not dominated by the effect of this model is not a background effect, because it's not a background effect because one of the daughter particle is still massive. So this means that we can keep the same value, we can keep the value of omega m constant with respect to lambda CDM model. We can have an omega m value which is quite similar to the lambda CDM model because one of the daughter particle is still massive. However, what we will change in this in the model with respect to the lambda CDM model is that we have a warm dark matter particle instead of a cold dark matter particle, and this will create a suppression in the galaxy power spectrum. Why? Because this warm dark matter particle has a pressure, okay, and at small scale the pressure is dominant with respect to the own gravity of the warm dark matter. So at some point, at small scale, we will decrease the clustering of matter and the clustering of galaxies because of the pressure of the warm dark matter. So here again, I'm showing you the residuals of the monopole of the galaxy power spectrum between this model and the lambda CDM model. And we can see that tau still controls the separation, but now epsilon controls the beginning of the separation. Namely, the lower epsilon is and the later the separation. Because epsilon, which corresponds to the energy transferred to the dark radiation, or similarly to the energy transferred to the, we can deduce the, with epsilon, we can deduce the energy transferred to the warm dark matter particle also. And this epsilon is related to the free streaming scale, which is the scale from which the pressure becomes dominant with respect to the matter. So epsilon is related to this scale, and that's why epsilon controls the beginning of the separation. Regarding the cosmological constraint, we can say that this model now could resolve the SA tension, because we have an overlap between the contour from Planck and the direct determination of the SA parameter. Here, so we again compare the constraint from the BAO F sigma 8 information with the constraint from the effective field theory of large-scale structures. And we can see that this time, EFT of LSS can improve the constraint on tau really significantly. And we can see it in the first column of this triangle plot. And also, the addition of the EFT of LSS changes significantly the best fit. And now we have a preference for a long life particle. While with the BAO F sigma 8 information, it was a preference for a relatively short life particle. So here is my second partial conclusion. So here we can see that the EFT of LSS can have some constraining power on non-trivial extension to lambda CDM model, and not only on the lambda CDM model itself on its canonical extension. And for the first model, this is not the case, but we have derived strong constraint on this parameter still with the BAO of sigma 8 information. And in the second parameter, there is a huge impact of this theory, and this model could resolve the SA tension even if we add the effective field theory of large-scale structure analysis. And some few words about the feature of this model. Here in the right panel, I'm plotting the suppression, the residuals of the linear matter power spectrum between the best fit of this model of the decaying cold dark matter to warm dark matter plus dark radiation model with respect to the lambda CDM model for several redshift. And as we can see, the suppression increase with the redshift because we produce more and more dark radiation particle and warm dark matter particle. So it will be really interesting to have data at small redshift, which will be the case of Euclid and DAISY, in order to probe the suppression at a really small redshift in order to differentiate with the lambda CDM model. And so finally, I'm going to talk about another non-trivial extension to the lambda CDM model and the constraints of the EFT of LSS on this model. So I'm going to talk about the early dark energy and its resolution of the H0 tension. So first, let me briefly recall what this tension is. It corresponds to 5 sigma discrepancy between the Suess and the Planck determination of the expansion rate parameter. And as for the SA tension, this is a discrepancy between the CMB determination of this parameter, assuming the lambda CDM model, and a direct determination of this parameter, this time using a supernovae with a calibrator, which is, for instance, the Cepheid for shoes, or the TRGB for some analysis. So if you want to solve this tension from the theoretical point of view, I mean, by changing the lambda CDM model, we need to understand how do the Planck data measure this parameter. So actually, what Planck measures is theta s, the angular acoustic scale at recombination. So theta s corresponds to the ratio between the sun horizon and the angular diameter distance. So the sun horizon corresponds to an integral over the cosmical history before the CMB, while the angular diameter distance is an integral over the history after the CMB. And this theta s depends on h naught throughout the angular diameter distance. What is really important to know is that this parameter is really, really well measured by Planck. So we cannot do whatever we want with this parameter, and we have to keep this ratio between the sun horizon and the angular diameter distance fixed. And if we want to solve the Hubble tension, there are two main ways. The first time is to consider early time solution. So we want to increase H naught, the H naught determination of the CMB. And to do so, we can decrease the sun horizon at recombination. So we can find a new physics at early time before CMB that will decrease the sun horizon. And especially if we decrease the sun horizon, then we need to decrease the diameter angular distance to keep this ratio fixed. And to do so, we need to increase, for instance, the H naught parameter. So one of the best way to modify this sun horizon is to increase the value, the expansion rate of the universe before the CMB by injecting energy before the CMB. A second way is what we can call late time solution. So to increase H naught, we can also, if we want, decrease the value of the energy densities at late time. However, it turns out that the data seems to include this late time solution, and especially the BAO measurements seems to exclude it. So here I'm going to present an early time resolution of this tension thanks to the early dark energy model. So this model corresponds to a scalar field, which is described by the standard Klein-Gordon equation with potential, which is a generalization of the action potential with a power of 3. Okay, the standard action potential has a power of 1 instead of a power of 3. So in this parameter, this is also an extension to the lambda CDM model where we add 3 new parameters. So in this model, we have first the critical redshift, where the early dark energy contribution is maximum. So in the right panel, you can see that this critical redshift is around radiation matter equality. So we have this critical redshift, and we have also the fraction of early dark energy at this critical redshift, which is basically the maximum. This is when the contribution of early dark energy is maximum during the cosmic history. And finally, we have a last parameter, which is just the initial field value of this scalar field. So in the right panel, as you can see, this potential is able to create a constant evolution of the energy density of the early dark energy, which behaves before ZT as a cosmological constant. So before ZT, we have a new cosmological constant that will increase the value of the expansion rate of the universe in order to decrease the sun horizon. And when the early dark energy is maximum, when we reach ZC, then we have this component dilutes faster than the radiation. And it needs to dilute faster than the radiation because we want to suppress this contribution before the CMB in order to don't modify the late time universe. Otherwise, this model would have been ruled out by the late time probes. So it has been shown that the early dark energy can resolve the Hubble tension if the fraction of early dark energy is 10% at a critical redshift which is around the radiation matter equality. And just a small comment is that the early dark energy slow down the evolution of the growing mode because we increase the expression rate of the universe before the CMB, which implies that we need to adjust the lambda CDM parameters, and especially to increase S8, NS, and omega CDM in order to have the same clustering as in the lambda CDM model. So here I'm showing a figure which shows that the early dark energy could resolve the Hubble tension if we consider the combination of data of Planck plus BAO plus Pantheon plus a Schulz prior. So here in our work, the goal was to combine the EFT of LSS analysis of the Bose data to this dataset, Planck plus BAO plus Pantheon plus Schulz, in order to see the impact of this theory on the resolution of the Hubble tension by this model. However, some previous analyses have found that the EFT of LSS of Bose data ruled out the parameter space that resolves the Hubble tension. And this is the case of this paper, for instance, where in gray they show actually the same data combination as the slide. And in blue, they add to this data combination the full shape analysis of the Bose data. This is what they call FS here. And we can see that if we add the full shape analysis, then we ruled out the resolution of the Hubble tension by this model. However, this exclusion was due to an issue in the normalization of the Bose window function. If you want, here they use wrong data because of a normalization of an issue in the normalization of the Bose window function. And especially here, I'm showing you either for the lambda CDM model or the early dark energy model, the constraint of Bose data only with the new data, so the good data, and with the old data, the wrong data. So in the first two lines, I'm showing you the new data, while in the two last line, I'm showing you the old data, the wrong data, if you want. And what is interesting is that with the wrong data, we found a value of AS on NS, which was really low with respect to the new data, either for lambda CDM or for early dark energy. And as I said to you before, we need, because early dark energy slows down the evolution of the growing mode, we need to increase NS, but also a bit AS in order to compensate the clustering we observe in the lambda CDM model, in order to recover the clustering we observe in the lambda CDM model. So because this old data had a low value of AS on NS, we exclude with this data the resolution of the Hubble tension by the early dark energy. So here the goal was to redo the analysis with the good data and with the new data. And here I'm showing you, so here in blue contour, the red contour, sorry, corresponds to the grid contour here and the red contour here, okay? And in the orange contour, we add the EFT of LSS analysis of the Bose data. And we can see that EFT of Bose data provide little additional constraining power on F on this model of about 10% over the standard BAO F sigma 8 information. And this is not significant. And this does not allow us to rule out the early dark energy resolution of the Hubble tension. So here, the EFT of LSS has a small constraining power, okay, and we still resolve this tension by the addition of this theory.
Let Théo,
me. Yes.
Théo, we're running out of time. If you can wrap up.
Yeah. Okay. Nice. Okay. So I'm finishing. Okay. So yeah. So I'm skipping the ACK data because we can also resolve the early dark energy with ACK data alone, but I'm going to skip it, and I'm going to go throughout the conclusion. So we can say that the EFT of LSS does not rule out the early dark energy resolution of the Hubble tension, as it was shown in some previous analysis. And especially, it was the case for the HAG data. EFT of both data can provide sometimes stronger constraint over the BIO of sigma 8 analysis for the most extreme model of early dark energy. So it still has some constraining power, but this is not significant to exclude the Hubble tension resolution of this model. And just a few comments on the right, on this figure in the right panel, is that this model is able to accommodate the galaxy power spectrum. And as you can see, the error bar are still large. So when we will be able to decrease this error bar with the next generation of survey, then we will be able to differentiate between the lambda CDM model and the early dark energy model. So thank you very much for your attention. I think that I finished.
Okay, thank you. Thank you for the great talk. Are there any questions in the audience? I see there's a few hands raised. I don't know if these are. Yeah, please go on. Ben, I think it was first, or
I'll also begin, but I can go first. So you show predictions from class, and you were comparing them to the EFT of LSS. So I always thought that kind of your 10 extra parameters that you have, they're mostly like noisance parameters. Or so if you make a prediction, doesn't it mean that you kind of have a model of how these extra parameters should look like? So how do you get those for the prediction?
You mean, sorry, my connection is not really good. You mean how we modify this nuisance parameter in the presence of an alternative model, right? This is the question.
Yeah, so you were showing a prediction. So I was wondering whether if you make a prediction, then I guess you would have to have some idea of what these noisance parameters are. But I always thought they were like,
if we consider an alternative model, right?
But I think some slides after that I think you were just showing like for standard lambda CDM. I think was it that one?
This one is for the lambda CDM model, yes.
Okay. So how do you get the values for these parameters?
Okay. So here we perform a standard MCMC analysis, okay, with the 6 standard lambda CDM parameters, and we put all these parameters as nuisance parameters in the MCMC. So we at the end we have the value of these parameters, but this is really a fit of the data. Actually, we can obtain this value from MCMC or from n-body simulation. Okay, but what we have done here is that we have taken this value as a nuisance parameter in the MCMC and we fit it to the data. So at the end, we have a real posterior on these parameters, and this is what the data prefers.
Okay, I see.
Thank you.
Okay, Miguel, you're next.
Yeah, thanks a lot for the talk. So I have a probably very naive question. So when you were talking about the S8 tension, you were mentioning that you sort of want to reduce the clustering, but then if you put radiation, that changes omega m. So you wanted to like reduce the clustering while keeping omega n more or less similar. And I think you mentioned at some point that, okay, so you have like this radiation model that also radiates warm dark matter, and that doesn't change omega m that much. But you also mentioned something about interacting dark matter, self-interacting dark matter, or something like that. You mentioned it just in the slide. Do you have any idea of? So first of all, why? So is there a reason why you prefer this over self-interacting dark matter, or also how could you choose like one model over the other or something like that?
Okay, so this model, so the decaying dark matter model and the interactive dark matter model both work very well to solve the S8 tension. Okay, so actually there is no way or no strong reason to prefer one model over the other. And actually, if we want to compare them, you just have to compare the chi-square value, the final chi-square value, if you want to see which models the data prefer. But actually, I think that, in my opinion, there is no strong evidence to prefer one model over the other one. And here we are just studying decaying dark matter model because it was it's a standard model to solve the S8 tension. It was just a choice if you want. But
Okay.
yes, interacting dark matter is also working very well to solve the S8 tension. So usually it's interacting dark matter with dark energy, for instance, because if you have an interaction between dark matter and dark energy, then you will reduce the clustering of dark matter because of this interaction, and you will be able to create a suppression in the matter spectrum. So this model works very well also.
Awesome, thank you.
Any other quick questions? Probably from people outside our group. If not, Ben, do you have another question? Quick.
I have a kind of a follow-up question. So you were showing that you had quite different results depending on whether you used the West Coast or the East Coast priors. Doesn't that mean that your priors are maybe too informative? Or so how do you get those priors? And did you try to redo the analysis by kind of widening your prior, including both West and East Coast priors?
That's a really good question. So actually, so we have two different parameterization, and there is also two different philosophy, two different perspective of how we can choose those priors. So for instance, the West Coast decided to take into account only theoretical arguments. So in order to put their prior, they said, okay, we have in this formula here, we have here the three-level contribution, which is the first term. Actually, the first term, Z1 square times P11, is the three-level contribution of the galaxy power spectrum, while the other term corresponds to the one loop contribution. And so the theoretical argument is to say, okay, the one loop should be lower than the three-level. Otherwise, you break up the perturbativeness of this theory. So the West Coast decided to take priors on the EFT parameter such that we avoid the one loop to be higher than the three-level. So this is only theoretical arguments. For the East Coast, this is quite different because the East Coast parameterization, the East Coast group, have decided to take the priors from some simulation, and especially from some n-body simulation. So this is two different philosophy, two different kind of priors. Okay, so this is the motivation of those priors. Now, yes, we have indeed in this paper here, we have indeed tried to increase the range of the prior. And in fact, if we increase the range of the prior, we obtain better consistency on the best fit. But this is not the case actually for the 1 sigma region of the MCMC, because if you increase the volume of the priors, then you will increase the projection effect, because you will have something which is will have a posterior on the EFT parameter that will be really non-Gaussian if you increase the prior volume. So if you increase this range of the prior, you will increase the projection effect. So you will not have a better consistency on the 1 sigma region, but you will have a better consistency on the best fit, indeed.
Okay, I see.
Thanks. But if we take the same equivalent priors between both parameterization, which is not something which is really easy to do, because we have to perform the mapping, which is not really easy. But if you choose the equivalent set of prior, then you should obtain, of course, the same results.
Okay. Thank you.
You're welcome.
Okay, thank you, Théo. Thank you for the great talk and for accepting our invitation. Maybe we can
Thank you to you.
The recording and